Here's a fact that has decided real wars. Take two armies. One is just twice as big as the other, same weapons, same training, everything equal. Common sense says it's twice as strong, right? It isn't. It's 4 times as strong. Double your numbers and your fighting power goes up by the square. This comes from a model built during World War I by an engineer named Frederick Lanchester. Two forces, A and B, march at each other. Nobody gets reinforcements. Each side just chips away at the other, step by step, until one of them is gone. The rules are simple. Each turn, A loses a chunk proportional to how many enemies it faces. So the new A is the old A minus A times B. And by the very same logic, the new B is the old B minus B times A. Here, little a and little b measure how deadly each side's weapons are. Two coupled rules like this are begging to be written as a matrix. Stack A and B into a vector, and one step of the battle is just multiplying by this little 2x2 matrix, M. Run the battle n steps? That's just M raised to the nth power, hitting the starting vector. So the entire war, who wins, and how long it takes, collapses into one question. What does raising this matrix to a big power actually do? And that is exactly the job that eigenvalues were invented for. An eigenvalue is a special stretch factor. Along one special direction, multiplying by m does nothing but scale. For our matrix, the characteristic equation gives two of them. Lambda equals 1 minus the square root of A times b. And lambda equals 1 plus that same square root. And here's the beautiful part. Since A and B are both less than 1, the first eigenvalue is less than 1, so raised to the nth power, it fades to 0. The second is bigger than 1, so it blows up toward infinity. One direction dies out. The other runs away. The whole battle is a tug-of-war between those two. Split the starting armies along those two special directions, let the matrix run, and out drops a clean formula. A after n steps is one shrinking piece, plus one growing piece. Same shape for B. For large n, only the growing piece survives, so its sign decides everything. That growing term for A is positive exactly when A0 is bigger than the square root of A over B, times B0. Clean it up by multiplying through, and you get a strikingly symmetric rule. A wins when root B times A0 beats root A times B0. Now both sides of that are positive, so we're allowed to square them. And when we do, the model finally shows its face. B times A0 squared, against A times B0 squared. Your fighting power is your deadliness, times the square of your numbers. Look at what that's saying. Numbers show up squared. Deadliness shows up only to the first power. So doubling your troops multiplies your power by 4, but doubling how deadly each soldier is only doubles it. Concentrate your forces. Pays off quadratically. Let's actually run it. A starts with 100, B with 50, twice as many, but equal weapons. Watch the counts fall. B drops fast and faster, crashing to 0 in about 6 turns. And A barely bleeds. It ends with almost 87 troops still standing. Think about how lopsided that is. Twice the numbers, and it keeps nearly all of its army while B is wiped out. That's the square law in the flesh. And the model even tells you the clock, how many turns the whole thing takes, from a single formula with a logarithm in it. So a couple of difference equations, one little matrix, and two eigenvalues turn a hunch into a law. Concentration of force isn't a slogan, it's algebra. Bring more soldiers to the fight, and the mathematics rewards you by the square.